Okay, great. All right. Thank you, everybody, for coming to another MCRN Colloquium. Today we have Olivia Chandrasekhar here presenting on her PhD work. She's a PhD candidate at the University of North Carolina, Chapel Hill, and also Los Alamos National Laboratory, and an NSF graduate fellow. So I'm really excited to hear what you've been working on with regard to fire. And anything else you want to add, please do, and please take it away.
Awesome. Yeah, so I'm Olivia Chandrasekhar. Like Christian said, I work with Chris at UNC Chapel Hill. I'm a PhD candidate there. And then I'm also a research assistant at Los Alamos. So it's like a GRA position basically, and I'm mentored by Rodlin here. Um, and yeah, two things of note. One, I'm getting over a cold, so sorry if I have to clear my throat a few times. And then two, yeah, this is a run through for my PhD defense that is in a week exactly. And so I'll make reference a few times to my oral exam or elements of my written thesis, which some people here won't have seen, but hopefully that won't hinder understanding too much. Okay, cool. I'm going to, oh shoot, how do I do that? I'm gonna stop my video. Okay, but I'm still here, I promise. Great. So I'm going to talk today I'm sorry, I want to move this so I can't see it. How do I do that? Minimize it. Okay, great. I'm going to talk about my work for the last few years, which has been motivated by the desire to understand the mechanisms behind important fire phenomena without necessarily resolving all of the physics at hand. So I'm going to talk about some pathways to instability and models of fire propagation. And to context the work that I'm going to talk about, I want to start off. We're going to go to the next slide. Is that going to work? There we go. By giving a really brief overview of wildland fire modeling. So according to this guy named Andrew Sullivan, who is an Australian physicist and fire scientist who wrote several papers on the topic, historical modeling approaches can be broadly classified as empirical, physical, or mathematical analog models. So empirical models are going to use statistical approaches and data from experimental fires to come up with their governing equations. The famous Rothermel model, which was developed at the Northern Forest Fire Lab, which is now known as the Missoula Fire Lab in the 70s, is the prime example of that. Many of modern simulation tools that are still in use are actually based on these original equations from the 70s. And most of those empirical models are, in fact, quasi-empirical, and they have some basis in a physical framework. Physics-based models, as the name suggests, are based on the principles of physics and chemistry of fire. So they're often going to use massive computational resources to solve the equations of fluid dynamics on three-dimensional domains. These tools are really the state of the art right now, and fire tech out of Los Alamos is probably the foremost example. These models are extremely complex, and when they're used in scientific exploration rather than as a prognostic tool, they're often subject to a number of simplifying assumptions to allow researchers to study idealized situations. And unsurprisingly, my focus is going to be on these so-called mathematical analog models. And in these models, equations for fire spread are largely based on mathematical principles. So this could be like the principle of elliptical spread, level set methods, cellular automata, and reaction diffusion models. Now, in order for these to be analytically tractable, many of these approaches have to reduce the complexity of the fire system by a pretty dramatic degree. The benefit there is that they allow researchers to focus on the interactions of a limited set of physical processes and then study the resulting behavior in a rigorous manner. So in this thesis, I specifically focused on hydrodynamic and reaction diffusion systems that exhibit some kind of spatial pattern formation. And so I want to give some further background on that, on spatial pattern formation for further context. So I'm going to define pattern formation as a tendency towards self-organization in complex systems. And the study of pattern formation can be concerned with both the properties of the resulting spatial patterns and the mechanisms behind their formation. Alan Turing is known as the father of this field, and in his 1952 paper, which was titled The Chemical Basis of Morphogenesis, he wrote about pattern formation in biological tissues that resulted from the interaction between reacting and diffusing chemical elements in that tissue. So you can see an example in the skin coloration of this giant pufferfish on the lower right-hand corner. Another common example of pattern formation in reaction diffusion systems is vegetation patterns in an ecosystem that either has competing vegetation species or some kind of water or nutrient restriction. So the upper right-hand image shows this kind of pattern formation in aerial footage of the savanna in Niger. So pattern formation is also frequently observed in hydrodynamic systems, but the language that we use to describe it in that case is a bit different. So we generally talk about the transition from quiescent flow occurring in response to some changing parameter, which is often a non-dimensional quantity like the Reynolds number or the Prandtl number. And that's going to cause a bifurcation in the underlying system. And so a large number of hydrodynamic instabilities have been studied and classified, and they all have different mechanisms. So in the upper right-hand corner, we have a picture of the Kelvin-Helmholtz instability. I actually saw this in New Mexico the other day, but this is not that picture. This is a better picture. And this occurs when there's a shear between two layers of fluid that are maybe moving with a different velocity. In the lower right-hand corner, we have an image of vortex streets, which occur as a result of vortex shedding around blunt objects, in this case, islands. These are both seen in clouds in the atmosphere. Now, common to both of these kinds of systems is the idea that the onset of instability corresponds to the transition of the system from an equilibrium state, a stable state, through a marginally stable or threshold state, and then into another steady pattern state as some parameter is varied. That parameter could be a system parameter, like those non-dimensional numbers that we mentioned before, or it could be a wave number representing a spatial perturbation. What we're interested in is the identification of the threshold state, and then the study of the conditions that are going to lead to that state. So to provide the last bit of context in the next few slides, I'm going to introduce a handful of phenomena from the field of fire science that we believe can be understood through this lens of pattern formation. Okay. So first up is a phenomenon known as towers and troughs. So this refers to this pattern of coherent structures that emerges in the vicinity of a fire line inflaming, as opposed to, say, smoldering fires. They're characterized by this alternating pattern of updrafts and downdrafts, referred to as coherent streaks by some authors and towers and troughs by others. And that towers and troughs moniker comes from the observations of the phenomenon in landscape scale fires, like in the upper left image, where you can see these visible towers of flames and troughs that are devoid of flames. And these structures are actually observed across a wide range of scales, and so you can also see them in this image in the lower left-hand corner. These are in small experimental fires conducted in a lab. So similar pattern forming mechanisms have also been observed in radial spot fires. So the image on the right is from an experiment conducted at the Southern Research Station in Athens, Georgia. Researchers there used particle velocimetry data to track the evolution of a fire that was spreading radially outward from a point ignition under just calm ambient wind. That point ignition is indicated in red in these images. And so both the velocity, which is what we're looking at here, and the temperature data captured the disintegration of that original cohesive fire line in a ring into these discrete fire pockets that you can really see in the lower row of images, which apparently developed in response to instabilities in the underlying flow field. And those fire pockets actually appeared to be spatially confined to fixed points of the underlying flow. And the mechanisms by which they emerged weren't immediately evident to the authors of the study, but they did call for further investigation of the nonlinear system's dynamical behavior. Okay. So the primary question that we're going to ask is what physical mechanisms or properties underlie the pattern formation in the phenomena that we just talked about. And to that end, we're going to consider two different hypotheses. The first is that these pattern-forming instabilities arise as the result of thermally driven buoyancy and the fluid dynamics of the problem, which means that we should be able to observe them in a system that doesn't contain combustion. So viewed this way, the emergence of towers and troughs, for example, bears a resemblance to the formation of patterns of convective cells in Rayleigh-Benard convection. And that's when fluid is heated from below until the buoyant effects begin to dominate over the viscous effects, and then a pattern of convective cells forms. So I discussed this work extensively in my oral exam, and it's included as chapter 6 of my thesis. But to summarize for those who aren't familiar with that work, we explored a Rayleigh-Benard convection analog for fire propagation, where we represented the entire depth of the fire line as a hot plate over which fluid flows due to a wind turbine. We then found transverse pattern formation by way of a hot bifurcation. And the frequency of the patterns that we found was positively correlated with both the hot plate intensity and the wind. I've included some pictures of the eigenfunctions at marginal stability, so that threshold state of instability, that demonstrate the resulting pattern formation. So the majority of the work that I have done since then is on the second problem that I presented on in my oral exam, in which combustion does play a key role. That then leads us to hypothesis 2, which is that the interacting processes of diffusing heat and combustion are going to create the conditions necessary for instability and therefore spatial pattern formation. And so to that end, we're going to consider a reaction-diffusion model of fire spread. And the model that we consider has been used by other authors as a minimal model of fire propagation because it's known to admit these traveling wave solutions that we can use to represent combustion fronts. And we're going to impose a spatially dependent wind term that's not been considered by other authors, and that's meant to represent the local fire-induced wind and capture the physics of air entrainment. We'll talk about what that means. And we're going to ask if and how that wind term might destabilize the underlying system while still allowing for the existence of combustion fronts. Okay, let's introduce the model. So we're going to work with this PDE-based reaction-diffusion advection model. The first equation in U is for the temperature of the fire layer. We're going to define the fire layer as the region in which the fire is burning and then a thin layer of air directly above it. We've made the assumption that the gas phase and the solid phase of the fuel are tightly coupled, and we can just treat them as one. The second equation in V is for the mass fraction of fuel, which is defined as the quantity of fuel remaining at time t divided through by the initial mass of fuel available. And these equations have both been non-dimensionalized. Now that equation for temperature has elements of diffusion, advection due to the wind velocity, denoted W, a heat source due to the combustion reaction, and then a heat sink due to heat loss to the surroundings. And the coefficient on that heat sink term is L. That's the heat transfer coefficient times the Arrhenius constant, which is just the activation energy for the reaction divided through by the universal gas constant. We're going to fix that value throughout this talk at L equals 0.027, and that's based on the value used by the authors of the paper that we modified this model from. Our reaction rate is going to be defined so that if the temperature of the fire layer is at or below 0, which just refers to ambient temperature because we've non-dimensionalized, then there's no reaction. But as the temperature of the fire layer rises above the temperature of the surroundings, that reaction is going to proceed like e to the negative 1 over u. And lastly, this parameter beta is proportional to 1 over the heat of the reaction. So we expect for beta to be a small parameter because the process of combustion causes a large, rapid change in the total heat content of the system. And we'll discuss the implications of this being a small parameter in a moment. First, I want to clarify several important assumptions on our wind term. So the wind is going to be a vector. It's going to have components in the x and y directions. The y component is going to depend only on the y spatial coordinate. The x component, on the other hand, will depend on the x coordinate and time. And that's because we're going to pick the form of the x component of the wind to model what we'll call the fire-induced wind, which we'll discuss in depth soon. But for now, all we need to know is that the wind needs to be defined in the frame of reference of the moving fire front. So in a moment, we're going to transform our equations with a change of variable z is equal to x minus ct. Wx is going to become wx of z, a function of the traveling variable z. Therefore, in the stationary frame, it has to be a function of x minus ct. I just heard a Sakoko boom. Maybe somebody else came in. Okay. So solutions to the equations that we just presented are going to be these functions, u and v, that are themselves functions of both spatial dimensions and time. We're going to be interested in traveling wave solutions that move with some speed c. And so we can convert to traveling coordinates through this change of variables and arrive at the transform system in u tilde v tilde. And going forward, we're just going to be dealing with that system in traveling coordinates, and so I'm going to drop the tilde notation for simplicity. So these are our transformed equations in the traveling frame. Traveling wave solutions to this system are going to have the form of a pulse in the temperature. So they're going to connect regions of cool, unburned fuel, as on the right-hand side of this image, to regions of burned fuel that's cooled down completely, as on the left-hand image, or left-hand side of the image. But they're going to move through a region of hot, burning fuel along the way. So depicted in the original coordinates, they're going to look something like this, where we have this sharp leading edge gradient in the temperature, indicated in red, followed by a gradual cooling on the tail end, indicated in blue. Now, in the traveling frame, these pulse solutions are stationary. They don't change in time. Also, at equilibrium, they're homogeneous in the y direction, which means that we can describe the pulse solutions by this reduced set of ODEs. Now, lastly, the fact that this reaction is going to occur at a much faster timescale than the fuel consumption is what is causing this asymmetry in the pulse. So the cooling process is reliant on fuel consumption. That takes a really long time relative to the initial increase in temperature. That's because of that small parameter beta that only multiplies the fuel consumption dynamics. So this separation of timescales means that we have a singularly perturbed system. So we're motivated to take that small parameter beta to 0 and consider only the dynamics occurring on what we call the fast timescale. The effect of doing so is to essentially zoom in on the reaction part of the pulse. And these are now the front solutions that we will study. Another effect is that the derivative with respect to t of the fuel consumption v is 0, so we can treat v as a parameter. We're going to call it v star going forward. Now, a few last words about these front solutions. They're going to connect regions of burning fuel with regions of unburned fuel. They consist of these profile solutions in the z direction. We're going to call them u hat of z. Those are indicated by the dashed purple line in this schematic. And when we discuss the streamwise problem, we're going to be talking about these solutions and the dynamics in this direction. We also have some thickness in the y direction, and at equilibrium, that solution is homogeneous in that direction and is indicated by the solid purple line. When we discuss the transverse problem, we'll be talking about these solutions and the dynamics in that direction. Lastly, classical theory is going to tell us that these fronts are stable to 2D perturbations when that wind term is constant in space. So these traveling wave solutions can be thought of as heteroclinic connections in phase space that asymptotically connect fixed points of the equations governing the front solutions, which I've written here in first order form. Those fixed points can be found as zeros of this reaction term, v star r of u minus lu, which I'm just going to call f of u v star moving forward. So for v star above some certain threshold, it's 0.074, the reaction term is going to have three roots. Those are at 0, u equals u1, and u equals u2. The first root just represents ambient temperature. The second is the autoignition temperature above which the reaction becomes self-sustaining. And then the third zero is the maximum temperature that the reaction can reach given the initial fuel load, or rather that the fire layer can reach given the initial fuel load. So our traveling wave solutions will asymptotically connect the first and the last fixed points. And what I want to note is that in the image on the left-hand side, you can see that the red curve that corresponds to 0.07 is actually below the threshold for bistability, while the other two curves are above it. And in fact, for larger values of V star, closer to 1, those first two fixed points get really, really close together relative to that third fixed point, as we can see in this right-hand image. I know it looks like we just have two fixed points. There's actually three. So because we're interested in exploring the bistable regime, going forward, we're going to pick V star pretty small, so about 0.1, so that our fixed points are well separated and we're capturing that bistable behavior. Okay, so we're going to start off by linearizing our original PDE about these front solutions, these U hats. We're going to write it in linearized coordinates P instead of U. The linear dynamics are going to be sufficient to predict the local, but not the global dynamics of the nonlinear system. And so for ODEs, that's a result of the Hartman-Grobin theorem and the local stable manifold theorem. Bates and Jones extended these theorems to the infinite dimensional setting, so the PDE setting in the 80s. That linearization is going to allow us to study the spatial dynamics and the stability in each direction separately. Once we've done that, our separation of variables approach means that we'll be able to tie that information back together to say something about the 2D stability problem. So we're going to have a two-dimensional eigenvalue problem in these linearized coordinates. We can write P, our eigenfunction, as the product of Q and eta, which are each a function of only one spatial variable, Z and Y respectively. That's going to give us the streamwise eigenvalue problem, which I've indicated in blue, and then a transverse eigenvalue problem that I've indicated in purple. Now our streamwise eigenvalue is omega, our transverse eigenvalue is mu, and then our primary eigenvalue lambda is the sum of the two. Similarly, our streamwise eigenfunction is Q, our transverse eigenfunction is eta, and our full two-dimensional eigenfunction is a product of the two. Now our goal is going to be to understand the value of these eigenvalues and the structure of the two-dimensional eigenfunction when the primary eigenvalue is greater than 0. And it's worth noting that it's a self-adjoint operator, so we know that it's real, that eigenvalue is real. One thing of note is that we're going to look for stability in the streamwise direction because we want to find front solutions that are stable and will therefore persist as fronts. And we're going to look for instability in the transverse direction. That may lead to the formation of spatial structures in that direction along the length of the fire line. Okay, so we're going to start off by talking about the streamwise problem. And the first thing that we need to do is to construct the form of the streamwise wind. So it's well known that fires generate a local wind field as a result of entrainment of cool air. And that local velocity is referred to as pyrogenic flow by some authors and fire-induced wind by others, and that's the term that we're going to use. Basically, what happens is that as air is heated by the combustion reaction, it rises and cooler, less buoyant air is pulled in to replace it, as illustrated in this graphic that I pulled from an article in the Fire Technology Journal. Now, when we have a straight infinite fire line, which is what we're considering, the strongest effects from this entrainment are going to be in front of and behind the fire line. And that entrainment ahead of the fire line is going to occur in opposition to the motion of the fire line. So if the environmental and fire-induced wind are on more or less the same order of magnitude, the result is this wind term that switches in direction and possibly magnitude in space. We're going to model that with a step function, where the velocity for z less than 0 is alpha x, and for z greater than 0 is beta x. Using this definition gives rise to two potential situations that I've illustrated here. Either alpha x is greater than beta x or alpha x is less than beta x. And as a special case of the first option, we might consider the situation in which beta x is less than 0, which is less than alpha x, when that would result in a wind field that converges at the fire line. And so the fire line in these images is this little squiggly red line. Alternatively, as a special case of the second option, we could consider alpha x less than 0, less than beta x. That would result in a divergent wind field. So the first case is going to model that fire-induced wind that we just described. The second case isn't physically motivated, but it does provide a sort of relevant mathematical foil that's going to help us better understand the physical implications of our results. So the first thing that we need to do is consider the existence of solutions in the streamwise problem. And we know that in the constant wind case, traveling wave solutions are going to exist for some unique speed. We can call that speed c hat. And when c is equal to c hat, the unstable manifold from negative infinity and the stable manifold from positive infinity coincide in a heteroclinic orbit. A consequence of introducing a spatially dependent wind is that the systems at plus or minus infinity aren't the same anymore. So the two systems I have written here are the systems at negative and positive infinity, respectively. So C1 star here is equal to C minus alpha x. So alpha x is the magnitude of the wind at negative infinity. And C2 star is equal to C minus beta x, where beta x is the magnitude of the wind at positive infinity. But the wave speed value C for both systems is the same. Now, the addition of the spatial dependence means that our system has effectively gained an extra dimension. And in this case, the heteroclinic connections, and therefore the traveling wave solutions, correspond to an intersection of manifolds and not a coincidence of manifolds. The image on the right depicts the three-dimensional phase space. So the blue plane is the stable manifold of the fixed point at U20 for the system at positive infinity. So the second system I have written here. And the red plane is the unstable manifold of the fixed point 0 for the system at negative infinity. So the first system I have written here. The solid blue and red curves where those manifolds meet indicate the intersections of those manifolds with the plane z equals 0. And then we can take that point of intersection labeled by that black dot of the solid curves and trace it back across the unstable manifold and forward across the stable manifold to find the heteroclinic connection between the two fixed points. So these intersections and the resulting connections and solutions exist for a continuum of wave speeds in some range, and that's dependent on alpha x and beta x. And so our first result is going to be about those ranges. Okay. So let's start off by recalling that a convergent wind is going to correspond to alpha x greater than beta x. And we demonstrate that in this case, the intersections occur for a range of wave speeds c for c greater than c hat plus alpha x and c less than c hat plus beta x, where c hat, again, is the c value associated with constant wind. We can visualize those intersections by integrating forward from the fixed point at negative infinity and backwards from the fixed point at positive infinity. And I've depicted those results for alpha x greater than beta x here in phase space. So we're going to call these intersections type 1 intersections. On the other hand, a divergent wind is going to correspond to alpha x less than beta x. And in this case, we find that these intersections are going to occur for wave speed c in the range c less than c hat plus alpha x and c greater than c hat plus beta x. And again, we're looking at the results on the right-hand side for a range of solutions in phase space. And we're going to call these intersections type 2 intersections. So the proof for both ranges is going to rely on the sign of the derivative of the Hamiltonian when c star is equal to 0. I'm not going to go into too many details here, but you can find those details in our paper or in chapter 4 of my thesis. One thing I do want to note is the qualitatively different forms of the two kinds of intersections. So this intersection type looks pretty different from this intersection type. That's going to turn out to be a pretty key component in classifying their stability properties. Now, our second result is that type 1 intersections correspond to stable fronts and type 2 intersections correspond to unstable fronts. We can begin that proof by converting our system in Cartesian coordinates to polar coordinates. We find that the equation for the radial coordinate does not rely on the angular coordinate, and so we are allowed to just consider this single equation in theta, which is written here. And then the proof is going to rely on the fact that we have some intuition about the behavior of these solutions when omega equals 0 is an eigenvalue, and we can then use that to determine if it's possible for omega greater than 0 to be an eigenvalue. And we don't want that because we want spectral stability of these fronts. Again, there are more details about that in our paper and in chapter 4. Because we expect for stable fronts to persist as fronts, we're going to focus the remainder of our analysis on stable fronts that result from type 1 intersections. However, the work that we did in this section leaves us with a range of stable and therefore physically viable fronts, and no way of picking a unique front solution from that continuum of possibilities. And so what we need is some sort of selection mechanism to pick out the front solution. That's going to require us to solve the streamwise eigenvalue problem. But in order to do that, we're going to need access to really accurate representations of the profiles. So we're going to reframe the problem as a 2-point boundary value problem on the infinite domain, z and negative infinity to infinity. We're going to let beta x equal negative alpha x and then just fix that at some value. We're going to employ projective boundary conditions, which essentially just say that the projection of the stable manifold at negative infinity onto the space of solutions at that point has to be 0, and likewise for the unstable manifold at positive infinity. Now we know there exists a family of solutions indexed by the wave speed c, and in order to pick a single solution from this family, we're going to specify a phase condition. So that serves as an additional boundary condition that lets us specify the spatial location of the center of the profile. And imposing a phase condition means that we can leave the wave speed c as an unknown to be solved for. Now our results are depicted on the right, and they're color-coded by wave speed. Because our eigenvalue problem comes from linearizing our PDE about one of these profile solutions, having access to the solution is crucial for solving that eigenvalue problem. Now we're going to ask which of these profiles is the most stable. We're going to define what we call the preferred solution or the spectrally preferred solution across all possible wave speeds, or alternatively phase conditions, as a solution for which the largest eigenvalue is minimized. Now that's because the largest eigenvalue for each profile and wave speed combination is in some sense the least stable of all the possible eigenvalues associated to that combination. That's because that eigenvalue is the least negative, and the perturbations will therefore decay the slowest. Now we want to find the most stable of all of these least stable eigenvalues. To do that, we're going to turn to the angular formulation. Based on the fact that we have to connect the unstable subspace at negative infinity with the stable subspace at positive infinity, we're going to establish the following eigenvalue condition. We need the value of theta at the end of a solution trajectory initiated at this value of theta naught that I just put on the screen to equal this value of theta final. And as a sort of cartoon of the phase space in the angular system, we can imagine that we're trying to find the solution trajectory that connects the unstable manifold, indicated in red, with the stable manifold, indicated in blue, at negative and positive infinity, respectively. Another way to think of this is to define the accumulated angle, delta theta, as the difference between the necessary values for theta final and theta initial that I just had on the screen. So delta theta can be thought of the angle accumulated over the course of the theta trajectory. And because we always start from the same value of theta naught, in practice, we can also just look at the final value of theta. That accumulated angle is depicted on the right, again, color-coded by a range for a range of different wave speeds c. Now, a jump of size pi in that accumulated angle is going to indicate that the corresponding omega value is an eigenvalue for that particular set of parameters. That's because a jump of magnitude pi can only be achieved if our theta final value has moved from theta plus u, which is the unstable manifold at negative infinity, through to theta plus u plus pi, which means that it has to pass through theta plus s, the stable manifold at positive infinity, in the process. And it therefore has to satisfy the eigenvalue condition at that point. Now, an application of Sturm-Liouville theory is going to tell us that for each solution, this eigenvalue is the first in a string of eigenvalues ordered in decreasing size, and therefore the largest for that wave speed profile combination. Now, if we plot the largest eigenvalue for each profile wave speed pair as a function of the wave speed, as on the left, or as the phase on the right, we're going to get a curve with a clear minimum. The solution that corresponds to this minimum is the most stable and therefore the preferred solution. And one thing to notice is that both eigenvalue curves are essentially inverted parabolas, with omega only approaching 0 as gamma and c approach the limits of their respective ranges. And that's going to occur for the limiting cases of either c equals c hat plus beta x or c equals c hat plus alpha x. And that's at either end of that range of allowable speeds that we found earlier. And it's only for these limiting cases that an eigenvalue exists at or very near 0. And for all other allowable wave speeds, there's no 0 eigenvalue and therefore no translational invariance. All right, so the images on this slide depict the intersection of the stable in blue and the unstable in red manifolds for the preferred solution, as well as for two limiting cases on the right-hand side where the wave speed is on either end of the allowable range. The star in black in each image is going to correspond to the point on the profile where that derivative is maximized. That's the fire line. And then the dot clearly indicates the intersection of the manifolds, which corresponds to the location of the wind switch. So for wind speeds very near the ends of the allowable range, that wind switch occurs very close to plus or minus infinity and far away from the fire line. For the preferred solution, however, the wind switch is closer to the fire line than in either of the two limiting cases. And in fact, for that preferred solution on the left-hand side, we find that the wind switch occurs ahead of the fire line spatially in a manner that's consistent with the physics of air entrainment. And that's notable because we didn't explicitly model that wind field, and yet one of our key physical takeaways is consistent with the physics that we wanted to capture. Another interesting takeaway is that the preferred solution corresponds to a wave speed in absolute value of about 0.09, and that's larger than the absolute value of c hat, which is the unique wave speed, again, for solutions to the constant wind speed system. So what that means is that including a wind speed is going to induce a speed up of the front. Okay, so we're going to take a step back to the big picture for a moment. And remember that all of this work was done to understand what wind conditions would both reflect the physics of the problem and allow for front solutions that were stable in the streamwise direction and would therefore persist as fronts. And remember that those correspond to these one-dimensional streamwise profiles indicated as dotted lines in this schematic. We now want to understand the transverse spatial dynamics. And at equilibrium, those are pretty boring. They only have spatial structure in the streamwise direction, and so they're homogeneous with respect to the y-coordinate. But we're now interested in potential regions of transverse instability that might lead to the development of spatial patterning in the transverse direction. And to understand that, we need to solve the transverse eigenvalue problem, which is going to require us to decide on the form of that transverse wind term. All right. So to do that, we're going to go back to the towers and troughs phenomenon that I used as a motivating example at the beginning of the talk. And just to jog your memory, this refers to this pattern of updrafts and downdrafts that emerges along the length of a fire line. In our language, that would be in the transverse direction. And again, we can see that signature pattern in the flames of real fires, as on the left. We can also see that striping pattern in the vertical velocity output in simulations. So on the right is a fire tech simulation of fluid flow over a hot plate. And red represents regions of strong updrafts, and blue represents regions of strong downdrafts. And you can see that clear striping pattern. Now, the thing that actually causes this alternating pattern is a series of counter-rotational vortices that develop along the fire line and result in hot air being pushed up and cool air being pulled down, as in the schematic. So to capture the vertical pattern of updrafts and downdrafts in a one-dimensional setting, we're going to consider only the components of the velocity acting in the transverse direction. And you can see the projection onto the y-plane depicted in this figure by the purple arrows along the bottom. So the result is going to be a wind field that switches in space, similar to the streamwise wind. We're going to model that with a tanh function controlled by the parameters alpha y, beta y. We're going to be motivated to use a continuous function as opposed to that piecewise continuous function that we used in the streamwise case for two reasons. And firstly, it's just the smooth nature of this switch between values of positive and negative alpha reflects the physics more accurately than a step function. But secondly, these equilibrium solutions don't have transverse spatial structure. And so that means that we can use a more spatially complex wind without running into the complications regarding the existence of solutions that we encountered in the streamwise case. So our goal is going to be to determine if a transverse perturbation in the form of a non-homogeneous wind term, in this case that wind switch, can cause instability. So as a reminder, this is what we're trying to solve for eigenfunctions eta and eigenvalues mu. Written in first order form, it looks like this. And we're going to frame this problem again as a boundary value problem. And we can actually use the accumulated angle technique that we introduced earlier to get some intuition about where we might expect to find positive eigenvalues and to get good initial guesses for our spectral parameter mu. I'm not going to go into too much detail about that right now because I covered that technique pretty extensively in the streamwise case. But we can find the first positive eigenvalue by solving the first order system on an infinite domain with zero boundary conditions at plus or minus infinity, treating the spectral parameter mu as a free parameter. What we find is eigenvalues for a range of alpha y, beta y. I've plotted them here as a two-dimensional contour plot. So shades of red are going to indicate positive eigenvalues and therefore regions of instability. We can also find the eigenfunctions and the corresponding eigenvalues for some specific alpha y, beta y pair. So in this image, we're looking at alpha y equals 1 and beta y equals negative 0.5 for a range of initial guesses for the spectral parameter. The largest found eigenvalue is mu equals about 0.99, and that's going to correspond to the eigenfunction that doesn't have any zeros on the interior of its domain, the one that looks like an inverted parabola. And that's the one that we're interested in. All right, so we're going to go back to the big picture just one more time. We now have stability information for both the streamwise and transverse directions, indicated by the smiley faces. We want the primary eigenvalue, and that's going to be, again, the sum of the transverse and streamwise eigenvalues. And we need this to identify parameter regimes for which the primary eigenvalue is positive, meaning that the transverse eigenvalue has to be large enough to overcome the stabilizing effects in the streamwise direction. So we're going to fix beta x equals plus or minus 0.5 and let alpha y and alpha x vary. That's going to give us a picture of regions of transverse instability indicated by red in these images. So for positive beta x, that transverse solution is unstable for small alpha x generally and all alpha y. And then for negative beta x, the transverse solution is unstable for large alpha x generally and all alpha y. All right, so to find the two-dimensional eigenfunctions, p of zy, we need to find the product of the transverse eigenfunction, which we found a few slides ago, and then the streamwise eigenfunction, q of z. We can find the streamwise eigenfunction by solving for r in the angular version of the system, and then constructing a theta trajectory that satisfies that eigenvalue condition before converting back to Cartesian coordinates. On the left-hand side, we have a contour plot of the resulting eigenfunction in the boring case when both the streamwise and transverse winds are constant. So this results in a zero streamwise eigenvalue, a primary eigenvalue that's less than zero, a streamwise eigenfunction that's just the derivative of the profile, and then a stable front solution. On the right-hand side, however, we have a contour plot of the resulting eigenfunction when the streamwise and transverse winds are non-constant. So in this case, the primary eigenvalue is positive, and the eigenfunction is clearly localized in space in the transverse direction. We can also look at the two-dimensional eigenfunction for the parameters alpha x 0.05, alpha y 1, beta y negative 0.5. These were just chosen to be in those regions of instability that we identified. And on the right-hand side, we see two views of that eigenfunction for the largest transverse eigenvalue. These eigenfunctions are going to depict the local behavior of the linearized system in the vicinity of the front. And again, that linear behavior is sufficient to also predict the local dynamics of the nonlinear system. Now, the key takeaway here is that enforcing spatial structure in the spatially dependent advection term can then cause transverse spatial structure in the corresponding eigenfunctions, but only for those specific parameter regimes that we identified. Now, if we're looking at the largest eigenvalue and we only have a single wind switch, we're going to see a pattern that is essentially a pattern of frequency 1. We would see a higher frequency pattern with more wind switches, but the numerics, at least the way that we're doing them, get pretty complicated pretty fast. Another way to envision that higher frequency pattern is to just look at the higher order harmonics associated with, in this case, the second largest eigenvalue. Okay, so in conclusion, we sought to identify the physical drivers of pattern formation in systems describing propagating fire fronts. We proposed two different hypotheses and focused particularly on the second one in this talk. But in essence, the question boiled down to whether the onset of instability could be attributed to the interplay between diffusing heat and a combustion reaction, or to thermally driven buoyancy and the resulting fluid dynamics. And we did find regions of two-dimensional instability in both systems, which suggests that neither mechanism is solely responsible for pattern formation, and they both play a part. In the reaction-diffusion system, we found constraints on the wind term that allow for spatially patterned front solutions. And in particular, the fact that that the combustion system with constant wind is spectrally stable highlights the need for spatial patterning of the advection term in order to induce spatial patterning of the front. Okay, and with that, we'll see. Okay, that was a reasonable time. I will turn my video back on and take questions if I can figure that out. There we go. Okay. Hi again, everyone. Hopefully you can still see my screen.
Yes.
Oh, we had a few people hop in.
Perfect. First, thanks, Olivia. That was a great talk. It was really good. Very
Thanks.
interesting. And yeah, if anyone has questions, please feel free to ask.
So if I may ask a question, a very good talk. Thank you very much.
Thanks.
It was exciting. I mean, to me, this looks like new stuff, right? So my question is there any way that you can test these results? I see pictures of a controlled fire, and can you identify features of the fire that reflect what you found theoretically?
Yeah, that would be an excellent next step. And I think that the best way to do that would not be to be in an experimental fire, but would be using one of those really robust computational tools that I mentioned before. And so for the first problem that I talked about, actually the image, so the image on, let me just go up to the correct slide. This image here of this simulation on the far right side was me running simulations in FireTech to try and test the hypotheses that we developed for that first problem that I talked about. We haven't done that for the second problem, largely because we got really into the math. But I think the best way to do that would be to do it in a computational environment. I think trying to control for all those factors in a test fire would be really hard. And so that is definitely something that I'm interested in doing, because in those computational settings, you can sort of pick and choose the physics that you want to incorporate in a way that is maybe a little more robust in the way that we've done here.
Right. Okay, very good. Thank you.
Yeah. Hi, Caitlin. Nice to see you.
I have a question.
Daniel, I don't think I know you. Yeah, what was the other question?
Yeah, I mean, thank you for this very wonderful talk. You did a very nice. It was a very nice talk. So I mean, I've seen some of you. I've seen like versions of this talk, right?
Mhm.
So I just wanted some clarification. I mean, in the beginning, right? You talk about the Turing, you talk about Turing. Just talk about Turing, the 1952 paper, and so I wanted to discuss like how does your work, which you seek to identify like physical drivers of pattern formation, how does it differ from the typical Turing bifurcation that people do to study um, pattern formation?
Yeah. That's a good question. Well, so I believe the Turing bifurcation it's a supercritical pitchfork bifurcation usually. And so what we found in the Rayleigh Bernard convection problem was instability by way of a Hopf bifurcations. That was like pretty different. We didn't do explicitly a bifurcation analysis in this problem, but I think the difference here is that we're really looking at the effects of external forcing. So that wind term, like it's not like the wind term is a second equation that's coupled to the temperature. The wind term is something that we're externally forcing, and then we're asking how A, an external forcing, and then B, an external forcing that has spatial dependence is going to influence our stability. And so I think that's what differentiates this work from some other work in pattern formation.
A follow-up question, right?
Yeah.
So you discussed type 1 intersection and type 2 intersection. So you have stable front and unstable fronts. So can you give some clarification on how these two kind of correlate with each other? Just
Yeah, so sorry, I'm just writing down your first question because I think that's a good one. Yeah, let me go back up to this. So I should probably have these on one slide, but you can see the two. So type 1 versus type 2 just refers to whether we're looking at a convergent wind or a divergent wind. And that convergent wind, which I tried to motivate with this idea of a fire-induced wind, is what's really physically motivated. And thank goodness we found that those are the ones that are spectrally stable. And the ones that correspond to a divergent wind, which isn't particularly physically motivated, you'd really have to mess with your physics to get something like that, aren't stable and therefore just wouldn't persist as fronts. And the cool thing about that is that you can see that you have these sort of two different types of intersections. Like they look different. When Chris and I talk about these, sometimes we're like, it's this kind of intersection versus this kind of intersection. And when you're proving the stability of the two, you end up looking at the orientation of the tangent vectors. And you have like a positively or a negatively oriented basis. And that is really what technically defines the two different kinds of intersections, and then also plays into the stability properties. But I guess to answer your question, it's just convergent versus divergent wind.
I mean, does it have any effect on the pattern formation also?
Well, so we don't even really look at the second kind because our pattern formation is occurring in the transverse direction, like along the length of the fire line. But we need these fronts to actually exist and to be stable to perturbations to even be looking at combustion front solutions. And so those type 2 intersections correspond to unstable combustion fronts. So we don't even consider those because what's going to happen is it's going to get perturbed and then just dissipate or do something else insane. So we're only looking at the type 1 intersections because we want to have these combustion fronts.
Well, thank you. Thank you. That's it.
Yeah, those are really good questions. Thanks, Emmanuel. That's helpful. Anyone else?
Yeah. Are there properties of real fires that you don't think would be able to be captured by the reaction combustion system you've been looking at?
Yeah, so many. I mean, as I discussed at the beginning, this is really a simplification. And in fact, one thing that I would really like to look at is even just the original system that does have that fuel consumption. And I talked about how we're really just looking at the dynamics of the temperature. And so that's a big one. But just, I think a really, really important effect that would be relatively easy to incorporate into this is the effect of curvature. So we're thinking of this like straight infinite fire line, and we're talking about these effects of entrainment ahead of it and the motion of the fire line behind, but like really no fire line looks like that. It's like, I guess my arm doesn't bend that way, but it's parabolic at least. And that means that you've got like some really interesting effects in terms of this effect of pulling in cool air that we're just not capturing with a straight fire line. So that would certainly be probably the first thing I'd want to incorporate. That's also a really good question. Thanks, Blake.
Thanks.
Anyone else?
Just maybe one quick one. So it was kind of interesting to think about, if you could set up an experiment, as Hans mentioned, to try to control these things, and then also what can it capture. So for kind of thinking of both of those things, I don't know what kind of data sets are available, but I wonder, if there had been a prescribed fire, and I don't know if you had some measure of fire intensity spatially and a time series of that. That maybe it's more complicated than the model currently, or about as complicated, because some fires do sort of move roughly linearly. Do you think there'd be any use in using some kind of like data assimilation scheme to do a parameter estimation, see how well you could reproduce the data with the model after doing such a parameter estimation, something like this, like to try to get a sense of like.
Yeah. I do not think that this is the best model to use in a modeling sense that way. I think that if you are trying to fit data and you are trying to use it as I described, a prognostic tool, instead of saying, okay, can we understand the mathematical mechanisms at play and how they relate to the physical mechanisms? I think you'd be better off using certainly a model that has elements of what we talk about here, right? Because there's pretty like reaction and diffusion, those things are happening. But you would be better off using a slightly more complex model. And so we've got some tools that people at Los Alamos are working on that I think would really benefit from a data assimilation approach. And honestly, I don't think we really do very much data assimilation here. And so that would be interesting because I think that if you had a model that was maybe what I talked about, plus a few different kinds of species of fuel, plus oxygen consumption, say. Like even just adding in a little bit of complexity, I think that kind of thing. And then again, probably what you would want to do would be to train it, or to not train it, but to tune your parameters on simulation data. But you could also, there's certainly plenty of data sets from prescribed fires as well. But to answer your question, I think that this is not the best tool for that kind of modeling.
Okay. Okay, yeah, it's always an interesting interface, I think, between reduced order modeling and then I don't know how complex a system might be, because the reduced order models are really powerful in gaining understanding. And sometimes I've seen some where we've been surprised at how good they actually were. You had to like have very free parameters, and
Yeah,
you have to try to interpret what that means, but
yeah.
and whether it's even significant. But it's kind of, yeah, that's an interesting thing. Sorry, that's why.
And yeah, I mean, I'm definitely really interested in that because I mean, I obviously like working with these models that you can sort of manipulate and work with. And I think it's really, really powerful when you can look at them and say, like, no, we actually really understand what's driving this kind of thing. And you can only really do that in something as reduced order as what I'm looking at. But that sort of question of like modeling at scales, like how coarse scale can you get something before you just can't capture the physics anymore? I'd say coarse scale in like a theoretical way, not in a grid sort of way. I think that's a really interesting question. Yeah, something I'd be interested in looking more into in the future.
Cool. Okay.
Anyone else?
If I may follow up a bit. So
Yeah.
I know we all like to work with models, but the question is, how real are they? Right?
Mhm.
It's a legitimate question. So my question is, have you ever presented this to people, to firefighters?
And not to firefighters, no, but the work that the group that I work with at Los Alamos is a fire modeling group. And so when I give this kind of talk to them, I oftentimes get a lot of feedback on like, well, is this physically relevant? Blah, blah, blah. But one of the reasons why this work was originally sort of born, the reason why we came up with this was because we're trying, like the people who work on some of these models in my team here are trying to find ways to, instead of have these like really complex CFD models, they're trying to come up with kind of clever ways to capture different phenomena. And so they wanted an understanding of some of those towers and troughs that I talked about and a better way to incorporate that into one of their faster running models. Because currently it's just really like kind of back of the napkin math. And so that certainly there's like positive reception there. I think if I presented this actually to wildland firefighters, I don't know how that would go. But the sort of chain of interaction is that there are people in my group who are developing like a graphical user interface for some of our modeling tools so that firefighters and land managers and whatnot can be like, okay, well, I have this kind of fuel and do it on their phone or something. And I'm going to do this kind of ignition and I want to, you know, understand how my fire is going to spread and if this is safe to do. And so that is sort of like the end goal, but I think there's lots of different people on that pipeline. And I'm like way over here.
Yeah. But you might you could imagine a situation that you show this to firefighters and they recognize certain patterns, right? You've emphasized pattern formation, but they deal with these kind of patterns and they may say, yes, that's what we saw.
Yes.
That's the kind of test I'm looking for, really.
I see. Well, yeah, and I guess the physical motivation for like the examples that I use are examples that people in the fire science community, which is separate from like the actual fighting community, but they're, you know, they're fire scientists. They see these things in nature and they are important patterns that show up time and again, and they think are really important in terms of how a fire spreads and how it ignites fuel and whatnot. And so in that case, yeah, I'm definitely working with things that are of interest to people who actually are like looking at fires and thinking about them in a less abstract way.
Okay, well, we're a long ways from reality, I'm sure. But
Yes.
right? That's the idea. Okay, thank you.
Bye, Alana. Anyone else? Okay.
Okay. Yeah, if not, let's thank Olivia one more time, and great talk, wonderfully presented. And
Thanks everyone for coming. I appreciate it.
and then I believe we have a talk next week as well, so we'll see you all then, and see you next time.
Thank you.
Bye.
Bye, everybody.